Operators in System Verilog and Verilog. In Verilog and System Verilog, operators are used to perform mathematical operations, logical comparisons, and bit-level manipulations. They are essential for describing how digital circuits behave. Operators are mainly classified into two types: unary operators and binary operators. Unary operators act on a single operand. Binary operators act on two or more operands. Let's start with unary operators. Unary operators. Unary operators work on only one operand. Most unary operators return a single bit output, except for bitwise not. Let's take an example. A equals 4 tick mark B 1010, or simply A equals 10. Now let's understand each operator one by one. Logical not. Logical not checks whether the value is 0 or non-zero. If the value is non-zero, it is treated as 1. If the value is 0, it is treated as 0. In our example, A equals 4 tick mark B 1010, which is 10, non-zero. So logical not of A becomes 0. Bitwise not. Bitwise not inverts every bit individually. 0 becomes 1, 1 becomes 0. So A equals 4 tick mark B 1010. Bitwise not of A becomes 4 tick mark B 0101. Reduction and. Reduction and performs AND operation on all bits. For A 1010, 1 and 0 and 1 and 0. Result is 0. Reduction OR. Reduction OR performs OR on all bits. 1 or 0, or 1 or 0. Result is 1. Reduction XOR. Reduction XOR applies XOR to all bits. 1 XOR 0, XOR 1, XOR 0. Step by step. 1 XOR 0 is 1. 1 XOR 1 is 0. 0 XOR 0 is 0. Final result is 0. Reduction NAND, NOR, and XNOR. These are just inverted versions of AND, OR, and XOR. Reduction NAND is not of reduction AND. Reduction NOR is not of reduction OR. Reduction XNOR is not of reduction XOR. Reduction NAND, method 1. 1. Reduction NAND 0, reduction NAND 1, reduction NAND 0, that is 1. Method 2. 1 and 0 and 1 and 0, that is 0. Now, not of 0, that is 1. Reduction NOR, method 1. 1 reduction NOR 0, reduction NOR 1, reduction NOR 0, that is 0. Method 2, 1 or 0, or 1 or 0, that is 1. Now, not of 1, that is 0. Reduction XNOR, method 1. 1 reduction XNOR 0, reduction XNOR 1, reduction XNOR 0, that is 1. Method 2. 1 XOR 0, XOR 1, XOR 0, that is 0. Now, not of 0, that is 1.
Let us understand the unary operators using System Verilog code examples. This is the example code for all unary operators. In this code, you can see a data type called logic. It is a System Verilog data type. 3 to 0 means 3 down to 0. That means there are 4 bits: third bit, second bit, first bit, 0th bit. So in total, 4 bits. A is the variable that holds these 4 bits. We will go deeper into data types in upcoming videos, so no need to worry about them now. Inside the initial block, we assign A equals 4B1010. Now we are performing all unary operators on A. In the code, you can see $display statements. $display is used to print messages and values in the output terminal. It is similar to printf in C or print in Python. Now let's run the code. Here is the output. But first, let's focus on the code. Logical not. $display, quotes, exclamation point A equals %0D, close quotes, comma, exclamation point A. Everything inside the double quotes is the message. Wherever you see %0D, the value will be printed. In this case, it prints the value of exclamation point A. Now look at the output. The first line shows exclamation point A equals 0. Bitwise not. $display, quotes, tilde A equals %B, close quotes, comma, tilde A. Here, %B means binary format, so the output is tilde A equals 0101. Similarly, all other operators are printed. Look at the output carefully and compare it with the code. You will clearly understand how each unary operator works. Understanding operators becomes very easy when you connect code with output.
All the examples we saw earlier were written in a test bench, but we can also write the same operations in design or RTL code. Here's the design code and test bench code for all unary operators. The module name is reduction ops. It has one input, A, which is 4 bits wide. All other signals are outputs. All outputs are 1 bit, except bitwise not, which is 4 bits wide, because it returns a multi-bit value. In the test bench, we apply inputs and check outputs. First, at time 0, we apply A equals 4B1010, and we display all unary operations performed on A. Display is used to print values. To print binary values, we use %B. To print decimal values, we use %D. Here, most outputs are 1 bit, so we can use either %B or %D. But for A and bitwise not, we must use %B because they are multi-bit values. Now, look at the output for input A equals 4B1010. You may not fully understand the time units right now. That's okay. We will learn that in upcoming classes. For this input, logical not is 0. Bitwise not is 0101. Reduction AND is 0. Reduction OR is 1. Reduction XOR is 0. Reduction NAND is 1. Reduction NOR is 0. Reduction XNOR is 1. Now, at time 10, we apply a new value. A equals 4B1111. For this input, logical not is 0. Bitwise not is 0000. Reduction AND is 1. Reduction OR is 1. Reduction XOR is 0. Reduction NAND is 0. Reduction NOR is 0. Reduction XNOR is 1. Now, at time 20, we apply another value. A equals 4B0000. For this input, logical not is 1. Bitwise not is 1111. Reduction AND is 0. Reduction OR is 0. Reduction XOR is 0. Reduction NAND is 1. Reduction NOR is 1. Reduction XNOR is 1. By applying different inputs and observing outputs, we can clearly verify how each unary operator behaves. Binary and multi-operand operators. In this category, we use 2 or more operands. These include arithmetic operators, bitwise operators, logical operators, relational operators, equality operators, shift operators, and concatenation. Let's start with arithmetic operators. Arithmetic operators are basic operations like addition, subtraction, multiplication, division, and modulus. Now let's take an example. A is equal to 4-bit 1000, which is 8 in decimal. B is equal to 4-bit 0011, which is 3 in decimal. C is equal to 4-bit 0100, which is 4 in decimal. Now we will perform arithmetic operations on these values. First, let's start with addition. A plus B. So 4-bit 1000 plus 4-bit 0011. If you do binary addition, you will get 4-bit 1011, which is 11. And 8 plus 3 is also 11, so it is correct. Now look at the code. Here, A and B are 4-bit values, but we declared two result variables. One capital R result is 5-bit, and small r result is 3-bit. When we run this, the 5-bit capital R result gives 01011, which is 11, correct. But the 3-bit small r result gives 011, which is 3, completely wrong. Why? Because the small r result does not have enough bits, so the value gets truncated. So always remember, if your result width is smaller, you will lose data. Subtraction. Now let's do subtraction. A minus B, that is 8 minus 3. The result is 5. In binary, that is 4-bit 0101. And if you look at the output, it matches perfectly. Now multiplication. A multiplied B, that is 8 multiplied 3, that is 24. Now here is the important catch. The result depends on bit width. If you store the result in 4 bits, you will not get 24. You will get a wrong value because of overflow. But if you use 5 bits or more, then you get 11000, which is 24. Correct. So in multiplication, always make sure result has enough bits. Division. Now division. A divided by B, that is 8 divided by 3. The actual answer is 2.66. In binary, it is something like 1.01010, goes on infinitely. But Verilog or System Verilog does not store fractional values. It only stores the integer part. So the result becomes 2, that is 5-bit 00010. So even if the actual answer is 2.66, you will only get 2. Modulus. Modulus returns the remainder. A mod B, that is 8 mod 3. This gives the remainder. When you divide 8 by 3, quotient is 2 and remainder is 2. So the output is 2. In binary, 0102. And if you look at the output, it matches. So always remember, bit width decides whether your result is correct or wrong. Choose correct bit width. And all the codes shown in this videos are written in testbench, not in design code. You can also use them in RTL code. Here's the simple example. This has 3 inputs, A and B of 4-bit width, OP of 3-bit width, output result of 8-bit width. A and B used to input the values ranging from 0 to 15, and OP is used to select the operation between A and B. If OP is 000 plus 011 minus 010 multiply 011 divided by 100%. The result is stored in result. To test this RTL code, we have a test bench which inputs the inputs and checks output. You may not understand the code completely. That's okay. We will learn in coming videos. Now let's understand arithmetic operators using 3 operands. In our example, we have A equals 4-tick B 1000, B equals 4-tick B 0011, and C equals 4-tick B 0100. Now we perform arithmetic operations on these 3 variables. Addition. A plus B plus C. So, 4-tick B 1000 plus 4-tick B 0011
plus 4-tick B 0100. If we calculate this, 8 plus 3 plus 4 equals 15. In binary, 4-tick B 1111. So if the result is 4 bits wide, the answer is correct. Subtraction. A minus B minus C. So 4-tick B 1000 minus 4-tick B 0011 minus 4-tick B 0100. That is, 8 minus 3 minus 4 equals 1. In binary, 4-tick B 0010. So the result is correct for a 4-bit variable. Multiplication. A times B times C. So 4-tick B 1000 times 4-tick B 0011 times 4-tick B 0100. That is, 8 times 3 times 4 equals 96. Now here is the important point. A 4-bit variable is not enough to store 96. Minimum required bit width is 7 bits. So the correct result is 7-tick B 110000. Modulus. Modulus works only on 2 operands at a time, so we cannot directly perform modulus on 3 operands like A%B%C in a single step. We can perform arithmetic operations on 2 operands, 3 operands, or even more, 100, 1000, no problem. But modulus is different. Modulus works only between 2 operands at a time. Arithmetic operators can work on multiple operands, but always remember, result width and operator rules decide whether your answer is correct.
Bitwise operators. Now let's understand bitwise operators. As the name suggests, these operations are performed bit by bit. These include bitwise AND, bitwise OR, bitwise NAND, bitwise NOR, bitwise XOR, bitwise XNOR, bitwise NOT. Let us consider A equals 4-bit 1100, B equals 4-bit 1010. Bitwise AND. A and B. So 4-bit 1100 and 4-bit 1010. We perform AND operation bit by bit. First bit, 1 and 1 equals 1. Second bit, 1 and 0 equals 0. Third bit, 0 and 1 equals 0. Fourth bit, 0 and 0 equals 0. Final result, 4-bit 1000. Bitwise OR. A or B. So 4-bit 1100 or 4-bit 1010. 1 or 1 equals 1. 1 or 0 equals 1. 0 or 1 equals 1. 0 or 0 equals 0. Final result, 4-bit 1110. Bitwise NOT. We already learned this in unary operators. It works on only one operand. Let's take A. A equals 4-bit 1100. Flip all bits. 1 becomes 0, 0 becomes 1. Result, 4-bit 0011. Bitwise NAND. Now, a common mistake. Many people think bitwise NAND is written as A tilde and B. That is not correct for bitwise operation. Bitwise NAND means not of A and B. Step 1. A and B equals 4-bit 1000. Step 2. Not of 4-bit 1000 is 4-bit 0111. Final result, 4-bit 0111. Bitwise NOR. Again, don't confuse with tilde or. Bitwise NOR means not of A or B. Step 1.
A or B equals 4-bit 1110. Step 2, not of 4-bit 1110 is 4-bit 0001. Final result, 4-bit 0001. Bitwise XOR. A XOR B. So, 4-bit 1100 XOR 4-bit 1010. 1 XOR 1 equals 0. 1 XOR 0 equals 1. 0 XOR 1 equals 1. 0 XOR 0 equals 0. Final result, 4-bit 0110. Bitwise XNOR. A XNOR B. 1 XOR 1 equals 1. 1 XOR 0 equals 0. 0 XOR 1 equals 0. 0 XOR 0 equals 1. Final result, 4-bit 1001. XNOR can be written using tilde, XOR, or XOR tilde. Both are the same.
Now suppose we have A equals 4-tick B 1100 and B equals 5-tick B 01010. Here, A is 4-bit wide and B is 5-bit wide. Pause the video for a moment and think how the operation will be done. Congratulations if you got it right. If not, let's understand it step by step. A is 4-bit. 4-tick B 1100, which is 12 in decimal. Now, to match the bit width of B, we add a 0 at the MSB. So A becomes 5-tick B 01100. It is still 12 in decimal. So the important rule is, if two operands have different bit widths, the smaller one is automatically extended to match the larger one. Zeros are added at the MSB side. This rule applies not only to bitwise operations, but also to arithmetic operations. So here, A equals 4-tick B 1100 is treated as 5-tick B 01100. Now let's perform bitwise AND. A and B, 5-tick B 01100 and 5-tick B 01010. Now do it bit by bit. First bit, 0 and 0 equals 0. Second bit, 1 and 1 equals 1. Third bit, 1 and 0 equals 0. Fourth bit, 1 and 1 equals 0. Fifth bit, 0 and 0 equals 0. Final result, 5-tick B 01000. Whenever bit widths are different, always matches the widths first, then perform the operation. Bitwise operations can also be performed on more than two operands. If the operands have different bit widths, first all operands are extended to the maximum bit width, and then the operation is performed. Let's take an example. A equals 4-tick B 1101. B equals 5-tick B 010111. And C equals 3-tick B 0111. Now first we match the bit widths. The maximum bit width here is 5, so all values are extended to 5 bits. A becomes 5-tick B 01101. B is already 5-tick B 01011. And C becomes 5-tick B 00011. Now let's perform bitwise AND on all three operands. A and B and C is 5-tick B 01101 and 5-tick B 01011 and 5-tick B 00011. Now do it bit by bit. First bit, 0 and 0 and 0 is 0. Second bit, 1 and 1 and 0 is 0. Third bit, 1 and 0 is 0. Fourth bit, 1 and 1 and 0 is 0. Fifth bit, 1 and 1 and 1 is 1. Final result, 5 tick B 0 0 0 1. Similarly, you can perform OR, XOR, NAND, NOR, and XNOR on multiple operands in the same way. This is the test bench code. Look at it carefully. Variable A is 4-bit wide. B is 5-bit wide. C is 3-bit wide. The maximum bit width is 5, so all the results will be 5 bits wide. Here are the outputs, results of each operation. AND output, OR output, NAND output, NOR output, XOR output, XNOR output, NOT output. Pause the video and look at them carefully. Now, this is the RTL code along with its test bench. Inputs: A, 4-bit wide, B, 5-bit wide, C, 3-bit wide. Outputs: all outputs are 5 bits wide because the maximum operand width is 5. Outputs include AND output, OR output, NAND output, NOR output, XOR output, XNOR output, NOT output. Using assign statements, we assigned each output to its corresponding operation. Pause the video and carefully look at these operations. Now look at the test bench. In the test bench, we assigned values. A equals 4B1101. B equals 5B10115. C equals 3B011. 1 means wait for 1 unit of time. This unit can be seconds, milliseconds, or nanoseconds, depending on the time scale, which we will learn in upcoming lectures. Then we displayed all the outputs. Pause the video and observe the results carefully.
Logical operators, as the name suggests, deal with logic, meaning true or false, or simply 1 or 0. This means logical operations always produce a single bit output, either 1 or 0. Logical operators include logical NOT, logical AND, and logical OR. Logical NOT. We have already seen logical NOT. It operates on only one operand. The symbol used is exclamation mark. Let's take an example. A equals 4-bit B1010. This is 10 in decimal, which is a non-zero value, so it is treated as logic 1. Now, NOT A equals NOT 4-bit B1010 equals 0. If A equals 4-bit B0000, this is 0 in decimal, so it is treated as logic 0. Then NOT A equals 1. So the rule is simple. If the value is non-zero, result is 0. If the value is 0, the result is 1. And this works for any bit width, not just 4 bits. Logical AND. Logical AND operates on 2 or more operands. The symbol used is ampersand ampersand. Let's take an example. A is 4-bit B1010, 10 in decimal, treated as 1. B is 5-bit B00000, 0 in decimal, treated as 0. C is 3-bit B001, 1 in decimal, treated as 1. Now A logical AND B logical AND C. Each operand is first converted to logic. A is treated as 1. B is treated as 0. C is treated as 1. Now, 1 and 0 and 1 equals 0. Logical OR. Logical OR also operates on 2 or more operands. The symbol used is vertical bar, vertical bar. Using the same values, A is 4-bit B1010, 10 in decimal, treated as 1. B is 5-bit B00000, 0 in decimal, treated as 0. C is 3-bit B001, 1 in decimal, treated as 1. Now, A logical OR B logical OR C. So A or 0 or 1 equals 1. In logical operations, we do not care about bit width. We only check whether the value is 0 or non-zero. And, most importantly, the output is always a single bit, either 1 or 0. So there is no need to worry about result bit width.
Look at this test bench code. Here we have three variables, A, B, and C. A is 5 bits wide, which is 20 in decimal. B is 6 bits wide, which is 40 in decimal. C is 8 bits wide, which is 100 in decimal. First, we displayed the values of A, B, and C. Then we performed the operation A logical AND, B logical AND, C. All three values are non-zero, so each of them is treated as logic 1. So the result becomes 1 logical AND 1 logical AND 1 equals 1. Next, we performed A logical OR B logical OR C. Again, since all values are non-zero, they are treated as 1. So 1 logical OR 1 logical OR 1 equals 1. Next, we performed logical NOT of A. Since A is treated as non-zero, logical NOT of A is 0.
Look at this design and test bench code. Design code. In the design code, we have three inputs. A is 4 bits wide, B is 5 bits wide, C is 3 bits wide. We have three outputs, AND out, OR out, NOT out. In the assign statements, AND out is assigned as A logical AND, B logical AND, C. OR out is assigned as A logical OR, B logical OR, C. NOT out is assigned as logical NOT of A. Test bench. In the test bench, we applied input values. Look at the console output. The results are displayed there. Pause the video and observe the outputs carefully. Key point. Remember, we can perform logical AND and logical OR on operands of any bit width, and we can use a minimum of 2 operands, but it can also extend to 2, 3, 4, 5, or even more operands. Also, keep in mind, in logical operations, we do not focus on the bit width. We only check whether the value is 0 or non-zero. Relational operators. The name itself suggests that these operations reveal the relationship between operands. These can also work with multiple operands, but working with multiple operands is not advisable as it increases complexity and reduces code readability. It is advisable to work on only 2 operands at a time. Later, we will also discuss how to work with multiple operands. Relational operators include less than or equal to, greater than or equal to, less than. Symbol is less than. Let A equals 4B1010, 10 in decimal. B equals 2B11, 3 in decimal. Now, B less than A returns 1 because B is less than A. A less than B returns 0 because A is not less than B. Now let us say we have a third variable. C equals 5B10101, 21 in decimal. If we write A less than B less than C, 10 less than 3 less than 21, what does it return? Pause the video and think. Over. Now listen. If you think 10 less than 3 is false, so the overall result is 0, you are wrong. It actually returns 1. Why? The compiler does not compare all 3 operands at once. It compares only 2 operands at a time. So first, 10 less than 3 equals false, returns 0. Then 0 less than 21 equals true, returns 1. So the final result is 1. Now let's change the values of A, B, and C. A equals 2B11, 3 in decimal. B equals 4B1010, 10 in decimal. C equals 5B0000, 0 in decimal. Now A less than B less than C. This returns 0. Why? A less than B equals 3 less than 10 equals true, returns 1. Then 1 less than 0 equals false, returns 0. So the final result is 0. Now you understand why it is advisable to operate on only 2 operands at a time. If you want to operate on multiple operands, it is advisable to use brackets. Instead of A less than B less than C, you can write A less than B, ampersand A less than C, ampersand B less than C. This checks A is less than B and C, and B is less than C. This will give the correct expected result. Greater than. Symbol is greater than. Let
A equals 4B1010. That's 10 in decimal. B equals 2B11. That's 3 in decimal. Now, A greater than B returns 1 because A is greater than B. B greater than A returns 0 because B is not greater than A. Here also you can use multiple operands, but it is advisable to use brackets. Less than or equal to. Symbol is less than equal to. Let A equals 4B1010. That's 10 in decimal. B equals 2B11. That's 3 in decimal. C equals 7B001010. That's 10 in decimal. Now, A less than or equal to B returns 0 because A is not less than B. B less than or equal to A returns 1 because B is less than A. A less than or equal to C returns 1 because A is equal to C. C less than or equal to A returns 1 because C is equal to C. Here also you can use multiple operands, but it is advisable to use brackets. Greater than or equal to. Symbol is greater than equal to. Let A equals 4B1010. That's 10 in decimal. B equals 2B11. That's 3 in decimal. C equals 7B001010. That's 10 in decimal. Now, A greater than or equal to B returns 1 because A is greater than B. B greater than A returns 0 because B is not greater than A. A greater than or equal to C returns 1 because A is equal to C. C less than or equal to A returns 1 because C is equal to C. Here also you can use multiple operands, but it is advisable to use brackets.
Look at this test bench code. We have 3 variables. A is 4 bits. Value is 1010, which is 10 in decimal. B is 6 bits. Value is 100100, which is 36 in decimal. C is 3 bits. Value is 011, which is 3 in decimal. First, we printed all 3 values. Now, we performed basic relational operations between A and B. A less than B. 1, because 10 is less than 36. A greater than B. 0. A less than or equal to B. 1. A greater than or equal to B. 0. So far, everything is straightforward. Now comes the important part, chained comparisons. A less than B less than C. This is not evaluated all at once. It is evaluated like this. A less than B, then C. A less than B, 10 less than 36, which is 1. Now, 1 less than 3, which is 1. So final result is 1. A greater than B, greater than C. A greater than B, then C. A greater than B, 10 greater than 36, which is 0. Now, 0 greater than 3, which is 0. Final result is 0. A less than or equal to B, less than or equal to C. A less than or equal to B, then C. A less than or equal to B is 1. Now, 1 less than or equal to C is 1. Final result is 1. A greater than or equal to B, greater than or equal to C. A greater than or equal to B, then C. A greater than or equal to B is 0. Now, 0 greater than C is 0. Final result is 1.
Here is the RTL and test bench code example of relational operators. Pause the video and analyze the code.
Equality operators, as the name suggests, are used to check the equality between operands. These include equal to, not equal to, case equality, case inequality. Equality operators can be used with multiple operands, but it is always advisable to use them only with 2 operands. Equal to. Symbol is double equals. This checks whether two operands are equal or not. If both operands are equal, it returns 1. Otherwise, it returns 0. Let's take an example. A equals 5 tick 00011, 3 in decimal. B equals 3 tick 100, 4 in decimal. C equals 2 tick 11, 3 in decimal. Now, A equals B returns 0 because they are not equal. A equals C returns 1 because both represent the same value. Now consider A equals B equals C. Pause the video and think about what this will return. Here, operations are evaluated step by step. First, A equals B returns 0. Now, 0 equals C, which is 0 equals 3, returns 0. So the final answer is 0. The same evaluation rule applies to all equality operators when used with multiple operands. Not equal to. Symbol is exclamation point equals. This checks whether two operands are not equal. If they are not equal, it returns 1. If they are equal, it returns 0. Using the same example, A not equals B returns 1. A not equals C returns 0. Case equality. Symbol is triple equals. In case equality, comparison is done bit by bit. All bits must match exactly. Even unknown x and high impedance values must match. Let's take an example. A equals 4 tick 10x1. B equals 4 tick 10x1. C equals 9 tick 00010x1. D equals 4 tick 00x1. Now, A triple equals B returns 1 because all bits match exactly. A triple equals C returns 1 because extra MSB bits are zeros and values match. A triple equals D returns 0 because bits are not matching. Case inequality. Symbol is triple not equals. This is the opposite of case equality. It checks whether two operands are not exactly equal bit by bit. If any bit is different, it returns 1. If all bits match exactly, including x and z, it returns 0. Using the same example, A triple not equals B equals 0 because they match exactly. A triple not equals C equals 0 because they still match. A triple not equals D equals 1 because bits are different.
Look at this test bench example code for equality operators.
Look at this test bench and design example code for equality operators.
Shift operators. Name itself says it's about shifting. These include logical shift operators and arithmetic shift operators. In logical, a logical shift treats the binary sequence as just a raw string of ones and zeros. It doesn't care if the binary pattern represents a positive number, a negative number. An arithmetic shift treats the binary sequence as a signed number, specifically in 2's complement format, where the far left bit is the sign bit that tells you if the number is positive or negative. Logical operator. These include logical left shift, logical right shift. Logical left shift. Symbol is double less than. In this, the bits are moved towards left by a particular number, and empty bit places created on right side are filled with zeros. Example: A equals 7B10101011. Let's shift it by 3. A logical left shift by 3. 10101011 logical left shift 3 is 0101100. Now let's shift with 5. A logical left shift by 5 is 0110000. Logical right shift. Symbol is double greater than. In this, the bits are moved towards right by a particular number, and empty bit places created on right side are filled with zeros. Example: A equals 7B10101111. Let's shift it by 3. A logical right shift by 3. 10101011 logical right shift 3 is 0001111. Now let's shift with 5. A logical right shift by 5.
Arithmetic shift operators. These include arithmetic left shift and arithmetic right shift. Arithmetic left shift is similar to logical left shift. Arithmetic right shift is also similar to logical right shift, but there is one important difference. In arithmetic right shift, if the number is a signed number and the sign bit is 1, it fills the empty bits with 1s. If the sign bit is 0, it fills the empty bits with 0s. Arithmetic left shift. Symbol is caps left, caps left. This is same as logical left shift. Append 0 on emptied places. Let's A equals 7B10101011. A arithmetic left shift by 3 is 01011000. Arithmetic right shift. Symbol is caps right, caps right. Here comes the different. Whether to add zeros or ones on empty bit places depend on whether number is signed or not. If not signed, add 0 on empty places. Like this. Let A equals 7B10101101. A arithmetic right shift by 3 is 000101101. If A is signed and sign bit, that is MSB bit, is 1, add 1s like this. A arithmetic right shift by 3 is 11110101. Let's say it's signed and sign bit, that is MSB bit, is 0, add zeros. Let's say A equals 7B00101101. A arithmetic right shift by 3 is 0000105.
Here we have one variable A of type logic, which is by default unsigned. That means you can't assign negative numbers to it. And we assigned 1010, which is 10. And we have another variable B, which is signed. That means we can assign negative numbers to it. We can make it signed by adding the keyword signed after the data type. Here, the data type is logic. We assigned -4, or 1100. We can also assign it as 1100 as well. In the initial begin block, inside the display statements, we are doing shift operations. First, logical shift operations. First, we displayed A. In line 13, we did a logical left shift by 3. And in line 21, we did an arithmetic left shift by 3. And the results are the same, 0, 0, 0, 0. In line 14, we did a logical right shift by 3. And in line 22, we did an arithmetic right shift by 3. And the results are the same, 0, 0, 0, 1. So when the variable is unsigned, the results will be the same in logical and arithmetic shift operations. But when it comes to signed numbers, logical left shift and arithmetic left shift are the same. In line number 16, we did a logical left shift. And in line 25, we did an arithmetic left shift. And the result is the same, 0, 0, 0, 0. But with right shift, it's different. In line 17, we did a logical right shift, and the result is 0, 0, 0, 1. In line 26, we did an arithmetic right shift, and the result is 1, 1, 1, 1. And the reason is that it's signed.
Pause the video and look at this RTL and TB code of shift operators.
Concatenation operator. Concatenation simply means join two numbers. Symbol is example. A equals 4B1100 and B equals 4B0011. Concatenation of A and B is 8B11000011. That's it. Simple. Let's add third variable. C equals 3B101. Then concatenation of A, B, and C is 11B110000111101. Now let Y equals 41B.
This means y equals 4b1111. Let x equals 22b10. Then x equals 1010. It's that simple. Now look at test bench code. Pause the video and look at it carefully. And try to understand the code.
Operator precedence. It is like the BODMAS rule in maths. If you don't know the BODMAS rule, first learn what it is, then operator precedence will be easy to understand. In BODMAS, we have rules where, in an expression, we operate based upon operation priority. We first compute what is inside brackets, then orders, then we do division, then multiplication, then addition, and at last we do subtraction. Example, we have x equals 2 plus 3 times 4. Let us compute. X equals 5 times 4, then x equals 20. But it's wrong. BODMAS says to do multiplication first, then addition, if brackets, orders, and division do not exist. We did addition first, so it's wrong. Now we do multiplication first, then addition. X equals 2 plus 3 times 4, x equals 2 plus 12, then x equals 14. This is right. Pause the video and check if this is right on a calculator. Similarly, we have operator precedence in System Verilog and Verilog.
Take the same example. X equals 2 plus 3 times 4. Without precedence, the compiler would not know whether to do 2 plus 3 times 4 equals 20, or 2 times 3 times 4 equals 14. Because when multiple operators are written in one expression, the compiler needs rules to decide which operation should happen first, which operation should happen next. Without precedence rules, expressions would become ambiguous. Here is the operator precedence of all operators in Verilog and System Verilog. Here is the operator precedence table. Look at it carefully. The top has high precedence, and as it goes down, the precedence reduces. Pause the video and look at it. You will learn what a ternary operator is in upcoming lectures, so don't worry. Now try to solve x equals 2 plus 3 times 4 using operator precedence. X equals 2 plus 12. Therefore, x equals 14.
Look at this test bench code. Try to solve yourself and check if you did correct. Here, instead of logic, we used integer data type. In upcoming classes, we will learn about all data types. We can also operate on binary numbers. Here, we used integers. For both, they work same.
Till now, we have seen examples of operators mostly using binary values. But in System Verilog and Verilog, operators can also work with different data types like logic, reg, int, integer, byte, and more. And instead of always assigning binary numbers, we can also assign normal decimal numbers directly. Example, logic 30A, A equals 2. Here we assigned decimal 2. Internally, since A is 4 bits wide, the value becomes 0010. So this, A equals 2, and this, A equals 4 bits 0010, both are the same. We can also use int. Example, int A equals 2. Here int is a 32-bit signed data type, so internally 0000, 0000, 0000, 0000, 0000, 0000, 0000, 0010. You can also assign values in different number systems. Example, int A equals 10, decimal, A equals B1010, binary, A equals HA, hexadecimal, A equals O12, octal. All these represent the same value, decimal 10. As long as the value fits within 32 bits, it is valid for int. Similarly, we can also use integer. Example, integer A equals 10, A equals B1010. A equals AH. Integer is also a 32-bit signed data type. Now let us talk about display statements. Till now, for binary printing, we used %b. Example, display %b, A. But we can also print in decimal using %d. Example, display %d, A. Even if the value was assigned in binary, we can still print it in decimal. Example, A equals 4B1010. Display %d, A. Output, 10. Similarly, even if the variable is int or integer, we can still print it in binary using %b. Example, int A equals 10. Display %b. Output, 000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 So the important point is, you can assign values in any number system. Assignment format and printing format are independent. Examples, A equals 10, display %b. A equals B1010, display %d. A equals AH, display %o. All are valid. One more important point. Int and integer are slightly different in System Verilog. We will learn the differences in upcoming classes.